In recent years, reasoning large language models have achieved breakthroughs in solving complex math problems, coding tasks, and logical puzzles. These models don't just answer questions, they think, step by step, using extended chains of thought. But this powerful capability comes at a steep cost: memory. Every time the model generates a new token, it must store a growing amount of information in its key value, KV, cache. For a model like Llama-3.1 generating 32,000 tokens of reasoning can require an extra 16 gigabytes of GPU memory, all due to the quadratic scaling of attention computation. This makes batch inference nearly impossible and severely limits real-world deployment. Existing methods for KV cache compression, like dropping less important tokens or reallocating full cache to certain attention heads, struggle with reasoning models. Why? Because they treat the KV cache as a passive storage mechanism, when in reality, it's the carrier of reasoning itself. When you compress it too aggressively, you don't just lose data, you break the logic. We've seen this in action. Token-dropping methods cause models to get stuck in loops, repeating the same phrases over and over. Head reallocation methods, which try to identify critical heads, often misidentify them. They focus on retrieval heads, designed for finding facts, not for maintaining logical consistency across a chain of thought. So here's the insight: not all attention heads are equal during reasoning. Some heads are essential for maintaining coherence, self-reflection, and logical progression. Others are expendable. We call these essential ones reasoning heads. To find them, we propose RLKV, a reinforcement learning framework that directly identifies which heads matter most for reasoning, by optimizing for reasoning quality itself. Here's how it works. First, we modify the attention mechanism to allow each head to dynamically choose between full KV cache access, the standard mode, or compressed access, which only keeps a small number of recent tokens and initial sync tokens. This is done through lightweight gating adapters, one per head, that learn how much each head relies on full cache. Then, we use reinforcement learning to train these adapters. The model generates reasoning traces, and we evaluate them based on whether the final answer is correct, a simple, verifiable reward. The RL objective maximizes this reward, while applying an L1 penalty to encourage sparsity. As training progresses, the adapters learn to assign high values to reasoning heads, the ones that must keep full cache, and drive others towards zero, meaning they can safely use compressed cache. But there's a problem. As the adapters become sparse, the reward signal becomes unstable. A model with too few reasoning heads fails more often, leading to sparse, unreliable rewards. Meanwhile, the L1 penalty remains dense across all parameters. This creates a vicious cycle. Poor performance right arrow sparser rewards right arrow stronger penalty right arrow even sparser adapters right arrow collapse. To fix this, we introduce two stabilization techniques. First, self-distillation sampling. Instead of training on the hardest problems, we filter out the ones the model already solves correctly, then curate a balanced dataset based on problem difficulty. This keeps the reward signal stable throughout training. Second, adaptive penalty weighting. We dynamically adjust the strength of the L1 penalty based on the model's current performance. If reasoning capability degrades, we reduce the penalty to prevent collapse. If performance improves, we increase it to push for greater sparsity. This creates a self-regulating system that avoids failure. After training, we rank all attention heads by their adapter values. The top few, the ones with the highest values, are the reasoning heads. During inference, we allocate full KV cache to these heads and compressed cache to the rest. The results? Remarkable. On two leading reasoning models, Llama-3.1 and Qwen-2.5-7BR1, RLKV outperforms all baselines across multiple benchmarks: GSM 8K, Math 500, AIME 24, and MBPP. At 40% or 60% cache sparsity, where other methods fail catastrophically, RLKV maintains near-lossless performance. In some cases, it even surpasses the full cache baseline, suggesting that by pruning noisy or redundant heads, we improve reasoning clarity. More importantly, we can now answer the question: which heads matter for reasoning? We conducted controlled experiments where we replaced the top reasoning heads with compressed cache, and performance dropped sharply. Replace retrieval heads. Much smaller impact. This proves that reasoning heads are not just important, they're essential. And compressing them is the single biggest risk. We also analyzed failure modes. When reasoning heads are compressed, models fall into repetitive loops. They lose track of their own logic. When retrieval heads are compressed, errors become more varied, but still, the reasoning process is disrupted. This tells us something profound. Reasoning is not a linear sequence of facts. It's a dynamic, stateful process. The KV cache isn't just storing information, it's maintaining the state of thought. And only a small subset of heads are responsible for that state. So what does this mean for the future? First, RLKV opens a new path to efficient reasoning inference. With 20% to 50% less memory usage, models can run on consumer hardware, support longer contexts, and enable higher parallelism. Second, it reveals a deeper truth. Reasoning models are functionally heterogeneous. Different heads play different roles. Some are for memory, some for logic, some for self-checking. Understanding this opens doors to better interpretability, model pruning, and even architectural design. And finally, this work shows that reinforcement learning isn't just for training models. It can be used to understand them. By using the model's own behavior as a signal, we can uncover its inner workings in a way that's both principled and practical. This isn't just about saving memory. It's about building smarter, more efficient, and more transparent reasoning systems, the kind that can scale to real-world challenges. The future of AI reasoning isn't just about bigger models. It's about smarter compression. And with RLKV, we've taken a critical step forward.